The last two sets of slides in this unit were sort of the grand finale of everything we've been doing because a whole bunch of ideas came back and collided, like solving linear equations with Gaussian elimination, like determinants, like spanning sets, like basis vectors. This particular topic here, diagonalization of matrices, is kind of like the encore. It's going to pick up on what we just learned and use it for a particular goal. There are some times in particular mathematical settings when we need to do a thing which I'll describe informally as redesigning the information contained in a matrix in a way that changes the matrix into a diagonal matrix. Now, a diagonal matrix, you should remember, is one that's got whatever entries it has down the diagonal, but zeros everywhere else. Now, you have done this before. When you do Gaussian elimination all the way down to reduced row echelon form on a square matrix, you try to do this. You try to take all the information in a matrix and distill it down into a diagonal result. So you've kind of done this conceptually before. What we're going to do is different than Gaussian elimination, but it's sort of the same idea. It's distilling a matrix to some essential information. What we're going to do here is called diagonalization of a matrix, not Gaussian elimination. It's a filtering process, and the filtering happens by taking the matrix you want to act on and multiplying it on the left and on the right by a related pair of other matrices. So the big question is, can we find some matrix that will be invertible? And having that inverse, then we can compute P inverse times A times P. P is the diagonalizing matrix for A, and when we're done with this matrix product, out will pop a diagonal version of A with its essential information distilled down to the diagonal elements. So A is diagonalizable if we can find such a diagonalizing matrix P. A matrix A isn't always diagonalizable, just like a square matrix might not have an inverse, right? So sometimes these are not always yes questions. Sometimes the answer is no, we can't do it. Now, given when I'm talking about this topic, and we're talking about distilling a matrix down to its essential information, you might be getting suspicious about something, and you should be. And here's the key. The square matrix A, which is n by n, will be diagonalizable if its n eigenvectors are all linearly independent. So here comes another topic back to haunt you. If it is, then those linearly independent eigenvectors of the matrix A will just become the columns of this matrix P that will do the trick. And then when we create P inverse times A times P, we'll get a diagonal matrix. And even better, when we're done, the diagonal entries of this new matrix will be the eigenvalues of the matrix A. We will have distilled it down to its essential information. And the positioning of the eigenvalues on the diagonal corresponds to the eigenvectors and their placement. So if if the eigenvector that goes with eigenvalue 3 was put in the second column, then the eigenvalue 3 will show up in the second diagonal entry once A is diagonalized. So here, we've used this example a couple of times already. Let's keep going with it. So we've looked at this matrix before. It's 3 by 3. We've discovered eigenvectors. Let's not repeat the whole story. We have a new question about these eigenvectors, though. Are they linearly independent? Now, you'll have to go back and remember what that means and how to test for it. But it turns out that, yes, these three eigenvectors are indeed linearly independent. Therefore, this matrix A can be diagonalized, and we will diagonalize it by using those eigenvectors. So here we go. The three eigenvectors are shown. One's in red, one's in blue, one's in some kind of weird purpley thing. But anyway, the three eigenvectors become the three columns of our matrix P, and P is the hammer that hits the nail of matrix A to diagonalize it. So remember, we want to do P inverse times A times P. So we have to compute P inverse. There it is. Another thing you have to remember. Good grief. And when we build P inverse AP, we end up with a diagonalized version of A, and just as predicted, the diagonal entries of this new diagonalized A are just the eigenvalues of A. It worked. Footnote, at this point in the term, don't find your inverses manually. Go use a calculator, Wolfram Alpha, Maple, anything you need to help you out. The setup is the important thing here, not the manual manipulations to find the inverse. Now, you might be getting suspicious because we've told this story already that if the matrix is diagonalizable, then we go look for its eigenvectors, and we use those eigenvectors in this acting matrix P that's going to diagonalize our matrix A, and the diagonal version of A is going to have the eigenvalues down the diagonal. Well, we would have found the eigenvalues in the process of finding the eigenvectors. So do we really need to go build P inverse AP every single time? And I would say no, we don't, because to get this process started, we need to have found the eigenvectors and so also eigenvalues of the matrix A. So once we've confirmed whether or not the eigenvectors are linearly independent, we already know what the result's going to be. If the eigenvectors are not linearly independent, then we quit and move on to the next problem because the matrix A will not be diagonalizable. If the three eigenvectors are linearly independent, then you know that A is diagonalizable, and you know that the diagonal version is going to have the eigenvalues down the diagonal. I'm not saying never compute P inverse AP. Do it a couple of times so that you can see how it works out and get that warm, fuzzy glow of satisfaction. But in a crunch, if you know what the result's going to be, and you're absolutely certain the process would work, then you might as well leap to the end. So quick example like that, let's consider two matrices named A and B. One will be diagonalizable, one will not be. Here's their information in terms of eigenvalues and eigenvectors. Figure it out. Which one's going to be diagonalizable? That means which matrix, A or B, has the set of eigenvectors that are linearly independent. It turns out that the eigenvectors of A are linearly dependent. If you look carefully at them, you will notice that 2 times eigenvector v1 minus eigenvector v2 produces eigenvector v3. Therefore, v3 is a linear combination of v1 and v2. These 3 eigenvectors are not linearly independent. So matrix A will not be diagonalizable. Matrix B is awesome. It's ready to go. We can diagonalize it. Now, we can go take the eigenvectors, use them as columns in a 3x3 matrix P, go find the inverse of P, calculate the matrix product, P inverse times A times P. But we already know the result is going to be a diagonalized version of B with its eigenvalues down the diagonal. And now you know what you're going to get. And so that's it. That's how you diagonalize matrices, and that is a wrap.